Good afternoon, good day, everyone. Welcome back. I hope you all had a good break and a bit of time to process the very informative panels we had this morning. And if you missed it, don't worry, the recordings are still available on Swapcard on the event platform for a while. Today, I'll be moderating our training panel, where we really have an all-star lineup in front of you. I'm pleased to have some of the authors from our upcoming Natural Refrigerants Applications and Practical Guidelines textbook, where Atmosphere worked with the German publisher VD to translate their popular German version into a globally relevant, improved English version. We're almost ready for publication, and we're just checking the final PDFs, and I'm very excited to see this all come together after actually more than a year of hard work. And I mean, there really is such a need in the market for one combined technical independent resource with technology neutral information. And if we can really remove the skills barrier for natural refrigerants, then wider uptake will be significantly easier around the world, even in regions where skills are still scarce currently. I mean, today our panel of experts will be sharing some insights into the textbook, as well as the latest technology in the sector and how it works to make sure that everyone keeps the industry knowledge sharp. First up, I'm going to introduce you to Professor Michael Kauffeld, who is not only one of the main authors of the book and authored several of the chapters, but also the editor. He'll be setting the scene and speaking about natural refrigerants. And yeah, I mean, he's spoken earlier, so I won't go into too much detail about his bio, but yeah, he's been in the industry for quite a long time. And yeah, over to you, Michael. Thank you. And thanks everyone else.
Thank you, Ilana. Yes, just for the background, Ilana made an interview with me last year when we only had the German version around. And then I was so silly to suggest that we make an English version, which showed that it's a lot of work. So yeah, natural refrigerants, applications and practical guidelines is the new training source for natural refrigerants. You see the picture of the front cover to the left. It's actually hopefully out for the Christmas shopping sale. So Armin, Thomas, Joe, please help us. Just a few words on myself. I joined the refrigeration and air conditioning industry when the CFC ozone crisis was just about in 1986. And we all know that the CFCs are no good any longer. But so are the HFCs. So we had that in the 90s while I was in Denmark. We were already in 1995 saying that HFCs should disappear. And we do say the same nowadays for HFOs. I've been trying to put this case for the last 4 years because there's no planet B. So we should save the one we have. And after the ozone layer and the atmosphere, now HFOs are threatening the water resources, which is not a very good thing. So how can we protect the climate? To get back to that issue, we can reduce, of course, the indirect greenhouse emissions by reducing the energy consumption. We can all try to apply thermal energy storage on the cold side, which is one of the most energy efficient and cost-efficient ways of storing energy. And we can, of course, reduce the direct emissions by leak-tight systems and reduce charge quantities, but we can also use low GWP refrigerants. And this last issue is what this book is all about. And of course, refrigeration and air conditioning can also help to mitigate climate change. Let's have a quick look at the education of refrigeration fitters around the world. This is just a graph showing the vocational education level around the world. And you can see here, there are some countries like Czech Republic, Switzerland, Luxembourg, the Netherlands, Sweden. They have a very well-defined vocational education training, but then there are other countries like Korea, Chile, or the US. I had the first year of working in the refrigeration air conditioning industry in the US in 1986-87, and I can tell you the level of some of those refrigeration technicians is way lower than what we see in Europe. Luckily, there are training courses available, and I will just show you on the next four or five slides a few of those. This is from UNEP. A lot of it is like training the trainers, so that in the different countries, the trainers can train the other technicians. And this is very helpful when applying natural fluids. This is from UNIDO, and you can see here in this slide on the left-hand corner, that's hydrocarbons, ammonia, CO2. The training is needed, and they also do the training. They also have some training on HFOs, which I think it's not necessary to do that any longer, but that's my personal opinion. This is from Karlsruhe. We have been featuring training on the job in refrigeration and also natural refrigerants for the last 70 years. But you also find companies offering trainings. Here's an example from Bitzer with their Schaufler Academy, where you can go and have on-site training, and a lot of their training focuses on ammonia, on hydrocarbons, on CO2. And then, of course, there are various companies offering online training. Because I worked half a year with Danfoss in 2008, I choose their online training as an example, but there are other companies also offering very good online training courses, or associations do the same, like ASHRAE, for example. Let's focus on the book, Natural Refrigerants, Applications and Guidelines. Here I have a list of the different natural refrigerants. And as you can see, they are all old candidates. Propane has been used in the early years of the last century as a safety refrigerant because it's odorless and it is not poisonous. And ammonia has been used ever since the very early days in the 19th century in refrigeration systems, and is still the #1 refrigerant in industrial refrigeration, but will also gain in other applications, as I will show you in a little while. This is the copy of the table of contents of the book, and I will today represent Michael Eckert. He has written the chapter on ammonia as refrigerants. Michael has been working with ammonia as refrigerant for over 30 years, but he said that his English is not good enough for a conference, so he asked me to take over his part. But he's the brain behind the ammonia chapter. This is also taken from the book. It shows an overview of the different refrigerants and how they perform with regarding to global warming potential, flammability, toxicity, and so on. The ideal refrigerant would have green boxes everywhere. And as you can see, there is no refrigerant which has green boxes everywhere. You have to live with some trade-offs, no matter what you choose. So now let's focus on ammonia. And the only drawback is its toxicity. And for some systems, the price might be higher. But in the long run, as I will show you, it might be cheaper than having an HFC system. Here are two examples from Aarhus in Denmark, where I used to live for 8 years. The top picture is from a shopping a large shopping center, and the bottom one is a conference center where we had the 1996 Gustav Lorentzen conference on natural refrigerants. Both buildings are air conditioned using ammonia in their chillers, and they have been doing this successfully for the last 30 years almost. Low charge is possible with ammonia systems. You can go as low as 30 grams per kilowatt. And then examples you have here in the picture, Scandinavian Congress Center, Selling Department Store, and so on, but also Copenhagen Airport or Heathrow Airport. And even the ISS, International Space Station, uses ammonia because ammonia is the heat transfer fluid with the best thermodynamic properties. That's why they use it on the ISS, despite the fact that it is poisonous. Here's an example from Michael Eckert's company. They built an ammonia system at a car manufacturer in Germany for their central canteen. The ammonia system is actually located in the basement. So the picture you see there is taken in the basement, and they have a ventilation system in case there is a leakage. But usually ammonia systems are very tight because ammonia stinks, and any little leak is located right away and fixed. So here are some of the facts of that system installed in 2015. They serve 5,000 meals per day. They have a medium temperature system based on ethylene glycol in liquid phase. They have a low temperature system working with CO2. And the interesting thing is what is popping up now at the bottom of the slide. The capital costs were approximately 20% higher than an HFC system, but the energy consumption is 0 to 5% lower. So the total operating cost is approximately 25% lower due to the easier service of the piping system and the lower refrigerant cost and the lower maintenance cost, because they don't have to go for leak checking every third month, as would be the case with an HFC system. This is another system which we installed at the KIT Mensa in Karlsruhe. The actual system is not using ammonia as shown on the slide, but the actual system is using propane, because we were not allowed to use ammonia there, because the intake of the ventilation system for this big building is right next to the container for the refrigeration system. And the picture shown here shows actually a container from Michael Eckert's company, whereas the system in Karlsruhe was built by another refrigeration fitter. The unique feature about this system is that we use ice slurry as the heat transfer medium, so we can have a largely increased storage density. We can reduce the pipe diameters quite a lot. And then for the low temperature rooms, we have carbon dioxide underneath. So this is a system which we proposed already in 1994 in Denmark while I was at DTI, and it took 20 years before such a system was built in reality using only natural working fluids. Indirect systems, they were quite popular with ammonia some 20 years ago. Linde built a lot of supermarkets like that. There were supermarkets in Sweden like that, and in Norway, I assume, Armin. They disappeared in the north and the middle of Europe due to the good properties of CO2 systems, which we will present after this presentation, Armin. But I think for the south of Europe or for Australia or other very hot climates, ammonia would still be a good option for supermarket systems. Another option would be this, because we see water loop systems popping up all around the world. We have water-cooled condensers in the display cabinets in the shop, and this water loop can, of course, also be cooled by an ammonia chiller, for example, in Australia or somewhere in the Middle East, where it's very hot in the summertime, where transcritical CO2 may not be the best choice. So this is one slide from a friend of mine from Australia, Stefan Jensen. He builds a lot of ammonia systems with his company, and they always build direct expansion systems. He doesn't like the pump circulation in big systems. So even big abattoirs, big slaughterhouses or warehouses, he builds with direct expansion ammonia systems. And I think that's something we will see also in the future more often, ammonia in direct expansion systems and air-cooled ammonia condensers getting smaller in internal volume to reduce the ammonia charge. The left-hand side of this slide shows you something from a propane system, but they went down to 5 millimeter tubing in the condenser, greatly reducing the charge of the system. And on the right-hand side, you see something which I already proposed in 1993 when working for hydroaluminum, that we could use aluminum for ammonia heat exchangers. And nowadays there are examples of companies offering microchannel heat exchangers for ammonia systems. You can use them safely up to a water content of about 10%, as long as it's copper and zinc-free alloys. That's all I had to tell about the book and this ammonia chapter. As a matter of fact, my very first project in 1986 was an ammonia system. Everybody else in that class in Washington, D.C. designed an R22 system, but I designed an ammonia system. And I got a comment from the professor, Dave Didion, that he liked the way I presented, but he doesn't like the choice of refrigerant. So, but yeah, ammonia, I think, is the #1 refrigerant when it comes down to efficiency. Thank you.
Thanks, Michael. You really showed that, Professor, for so many years later, and look at how far ammonia has come. I think you can stop sharing at this point. Just want to remind everyone of the questions at the bottom for the live discussion. Feel free to send them throughout. There's also a poll, but we'll check a bit later on that, the questions. But before we move on to the next one, I wanted to ask you, Michael, I mean, while I have you, it's actually, you were listing all the different trainings that's happening, and it's exciting that there's so much already happening in natural refrigerant training, but do you think that it's enough? Like, is there enough training happening specifically on natural refrigerants, or where is there still a gap?
No, I think there's nowadays, at least in Europe, enough training available on natural refrigerants. There's still a long way in the country where you come from, or other African countries for that matter. And also Latin America. But I mean, people are working on it. UNIDO is working on it. UNEP is working on it. So it's going to happen, the change to natural refrigerants. There's no other choice, because after the HFOs, there are no more synthetic molecules which are suitable for refrigeration systems.
I think Armin and I spoke about it yesterday.
A comment from Norway. I mean, what we are struggling, or what we are encouraging the young people to go into our sector, to feel that this could be part of a real contribution when you choose what will be your career in different levels. I mean, from the people installing this system, designing these systems and so on. Sometimes our sector is not very visible when the young people have to decide in which direction they want to go. So we will have many efforts in the next weeks, months to come, to make our sector visible to the young people, to show that we can contribute to the green shift by doing good installations, because heat pumps and air conditioning or heat pump refrigeration is very important, the transition away from fossil fuel. And that is not always known to the young people.
That's right, Armin. And we had a very good example in the 1989, 1990 at the University of Hanover, while I was a PhD student there. Nobody was interested in refrigeration as a subject in mechanical engineering prior to the CFC and ozone crisis. But when we started announcing that the students working at our institute, they could save or protect the ozone layer, we were overrun by students. So this environmental issue is something which is of great interest for the young people. And there, the refrigeration and air conditioning really has a case, and has had during the last 30 years.
Yeah, so it's not only the windmills and produce electricity, it's the usage, how to energy efficiently use it and save it. That's the important part.
We need a bit of an industry image makeover to make it a bit more attractive for young people. But I think it's not even just that. I think making it attractive, I think a lot of, like you said, a lot of people don't even know it exists. I mean, 10 years ago when I started in this industry, I remember I had my first entry question was like, what is the HVAC in our industry? And I had to Google search what that acronym stands for. I've never even heard about it. And it really is like that to this day. People don't really hear about it, but as you rightly said, it can make such a big difference in the world. So I think we need to encourage the young people, because I mean, sadly enough, it is, I think, like a lot of industries, a very old industry. I mean, and also just back in South Africa, there's not that many young people yet entering the industry. So you really need to, like you said, the training isn't the problem. It's actually attracting people in the first place. Well, when I grow up.
I'm sorry, Ilana. I have a nice slide showing this. Yeah, when I grow up, it's a slide which I prepared. Yeah, I want to design cars. That's what the young boys say. Or I want to build cities. Or I want to develop airplanes. But have you ever heard a kid say, I want to develop bridges? Yeah, I think the slide shows it all.
Very appropriate.
Yeah, but now I think we should hand over to Armin.
We should, very appropriate slide. I mean, I would hand over to Armin, but I think we just lost him. I'm not sure what happened there. He was on the call a second ago, but let's give him a few seconds. Otherwise,
oh, then I can
always
fill the. Yeah,
I
you
mean,
can always
wait,
talk.
yeah, I was gonna.
You're a woman. You can always talk. I know.
I would not take this to gender, but Armin has joined us again. No, I think it's always technological issues, no matter where you are in the world, even in first world countries. You could always just blame it on the Belgian weather, which is gloomy as always. But Armin is joining now, so let's see. If not, we can move on to Joachim.
But within the International Institute of Refrigeration, we try to do something about this with our career in refrigeration and air conditioning working group. So everyone is welcome to join that.
Great.
Armin,
are you
back?
Are you back, yes. Armin? Are you ready?
Sorry, my computer is sometimes doing some strange things, but I try to share my screen now.
Oh, is that what happened? You got kicked out? Well, I hope you can share it and stay in the call. Let's see.
Yeah, it's...
Because you want to talk about how to upgrade CO2 booster systems, which
yes,
I think is very useful.
I try to share the right screen, as you know.
You have so many. Aha, I think we're in business.
Sorry, it's there. It's very good.
Okay, over to you then. Let's get into it.
I try to get it back. Here we are. So yes, welcome to my part. And today I will talk about, of course, part of the book, but I just go into a training how to upgrade a CO2 booster system. So as Michael mentioned, we have completed now a new book. And as part of this, I would like to go into the booster system with CO2 and explain the baseline and how to do different kind of upgrades to move this energy efficiency into levels where then it makes sense to put these systems at different places around the world. So, as Michael mentioned, this is the book, and there's an extensive CO2 chapter, which has been implemented now in English. Originally, it was developed in Norwegian from the Norwegian Refrigeration Society, and then we further upgraded it and put it now into this book. So feel free to utilize it. And why are we talking about natural working fluids? This slide is known to some of you, but let's focus on carbon dioxide today because we can use it for many different applications, from mobile heat pumps, from commercial refrigeration to heat pump chillers and so on. The rest is also in the book, and just have a look. What is a booster system? A booster system is a combined unit. Previously, we had freezing application and chilling application separate. When this came together with CO2 in one loop, it is called a so-called booster system. And that's why people call it the booster. You have a low pressure. I take the laser pen. You have the low temperature compressor. You have a high temperature compressor. All these combined with different kind of temperature levels for the freezing of the goods and the chilling of the goods. All together, that's why we call it booster. Many of these systems do have heat recovery because we cannot afford to throw away the heat. We can utilize the heat, especially with CO2, where we can upgrade the heat to very high temperature levels without any effort. Of course, in some times we have to reject some heat to the ambient. That's mainly done in the gas cooler. Then we do some intercooling before we have a valve where we throttle down the high side pressure. We control the high side pressure with this valve, go into an intermediate separator where liquid and vapor is separated. The vapor we send straight to the compressor. In this way, we are here now in 7. It's the separator. We are dividing liquid and vapor, send the vapor towards the compressor. That's why we just take out some of the heat, get the subcooling of the liquid, further subcooling of the liquid, which goes to all our evaporators, while the vapor is sent to the compressor. This is the basic booster system shown in the pH diagram with the main components and the main valves, which are implemented. Classic, simple booster system. 10,000 of these units are in supermarkets these days. If we go further, we can do an upgrade with a parallel compressor. Instead of sending this gas down from the 2nd floor to the 1st floor, we keep it in the first floor and send it up to the gas cooler, straight up. this is more energy efficient because we are not losing this exergy, and we can do this compression in a rather efficient low pressure ratio way. And the implementation is rather simple. In parallel to the flash gas bypass valve, which is controlling this pressure level, we have now a bunch of compressors called parallel compressors, which enable to maintain the pressure level here at this line. This is the main purpose of these compressors, to maintain the pressure level. And what we can do in addition now, when we have this new compressor stage, we can of course implement air conditioning. We can utilize this compressor power to do a useful work, for example, while implementing such a chiller into the receiver, which has the temperature and pressure level which fits perfectly for this kind of integration. The rest is the same. So this is kind of the implementation of a new compressor into the system, a new compressor part or suction group at the elevated suction pressure, which enables also the implementation of air conditioning. Next would be, I would like to highlight which different options do we have actually for air conditioning, because different building configurations require different approaches. And you see here we can have a air conditioning straight after the high pressure control valve, where we just send part of the two-phase flow into a chiller, which is then cooling water. That's one option. Second option would be to take some of the high side pressure towards into the building, wherever you have an air handling unit, where you have a DX evaporator. You can fill it, charge it with this via V2, expand it to the level of the receiver, and provide air conditioning with this. Second, as previously shown, self-circulation chiller is also possible. So these are different options, give the flexibility for these parallel compression systems to be implemented in different kind of buildings. When we go further, we can implement expansion work recovery. You may have heard about ejectors. We are utilizing some of this expansion work to do a useful job. In this case, and the simplest implementation is we have an ejector which utilizes this expansion work and sucks some of the vapor or some of the fluid from the medium temperature side, medium pressure side, back to the receiver level, and by doing so, enabling an extended operation of the parallel compressors. And in the same time, we can always utilize non-superheated conditions in the medium temperature and even low temperature evaporators, which is beneficial for the total energy efficiency. So this is another example how you further upgrade a system. And in addition, you can also do a simplification, because previously these kind of CO2 systems have been punished because it's too complicated, it's too difficult. That's why we said, okay, let's go back and propose a simple solution. This is what I want to focus now in the next minute, and then the rest is in the book. But however, let's have a look. What did we do? We have a simple system with the low pressure. We have a receiver here, but let's start from the compressor. We do heat recovery when it is needed. We reject the heat when we need to reject. We have a internal heat exchanger, and the high pressure gas goes to the port, the high pressure port of the ejector, which maintains the high side pressure in accordance to the temperature. So the ejector is expanding and at the same time sucks all the fluid, all the vapor from the medium temperature evaporators. So every chilled evaporator is connected to the suction port of the ejector, which brings this vapor back into the receiver, which is a low pressure receiver in this case. The compressor maintains the pressure level, and the liquid is supplied further to the evaporators, closing the loop. So, and in this case, we run it in a traditional way during the summer, and when we have enough performance in the ejector, this works like this. However, in case this is the active summer mode, as I just described, we run this valve is closed, nothing happens. It's traditional. In case we get to lower ambient conditions, the system can run as a traditional system, not in the transcritical mode. We can save a lot of energy by not having this high compression. And in this case, the ejector is not active. It's just a passive. The fluid out of the evaporator still has to pass through the ejector, but it does it without any action. And it comes back to the receiver and back to the compressor. By doing so, we send the liquid, the condensed liquid from the high side pressure towards the feeding wells of all the evaporators. And the main controller is managing this. So to maintain the high side pressure, to keep it at that level and feeding proportional to the different different evaporators. This works very well. We have tested this in our laboratory, and we do further implementations in the next field tests very soon. So these were just a few examples of how we can upgrade CO2 booster systems. You can read all this in the book, and if you can also download some ebook from our previous E2 project. So please, the floor is yours, and I'm open for questions. Thank you.
Thank you so much, Armin. Thank you for sharing. I think you can, glad your screens worked out in the end. Just a reminder again for everyone to submit your questions to the bottom there. I mean, there's been a lot of talk over the past 2 days about making these systems simpler and less complicated, especially on the CO2 side, which is good because I think I hear so often everyone saying it's too complicated, we can't train people on CO2. What is the most complicated in terms of CO2? Where does it, is it actually that complicated in terms of training, or is that just an excuse?
Actually, no, it's not so complicated because most of the people, at least in the field, they're very excited to get into this system and see the possibilities. And of course, as Michael also said, we cannot use one fluid for everything. And that you have to find the benefits of these systems. In some applications, flammability is not at all an issue. Then you can do other things. And in some cases, flammability is an issue. And CO2 is one of the last A1 or non-flammable, non-toxic fluids, which we can utilize. And when we then implement all the functions like cooling and heating at the same time, we can reach exceptional efficiencies, like in a hotel or somewhere else where you always need cooling and heating at the same time, maybe some intermediate thermal storage, but then we can find very nice examples. That's also one of the reasons why most of the supermarkets, when they do centralized systems, they go for CO2 because it makes it simpler in a way, and because the service, maintenance, all this stuff becomes much more simpler. But also at the end of the day, the energy bill is the key player, and it is more energy efficient because we can utilize the properties in a different way. We elevate the temperature levels. We bring it to the level where it is energy efficient and serviceable. The maintenance is possible, and the people know this fluid they can buy even in 20 years, even in 50 years. It's not a problem.
I think the energy saving and the lower life cycle cost is a great motivator to learn how to maintain a system.
The motivation. Yeah.
I think
of course, we need training to people understand that this is not rocket science. We have to follow the standards. If you follow the guidelines and the standards, we can build very safe system with hydrocarbons, with CO2, with ammonia. It's not a problem at all.
I think someone once explained to me, it's like you don't expect someone to just be able to know how to work on your car. You need to have training. And it's the same for air conditioning systems and refrigeration systems. They're so sophisticated. So obviously you're going to need to know how to work with them. And I think it comes to like actually people having more respect for the trade and that it is technical. Oh, thank you very much. I think before we move on to the next one, I'm not sure if everyone saw in the next to the chat box, there's also an option for polls. I put an easy one today. I think I made it difficult yesterday, and it was just, I'll check it again later. But so far, the question was, do you think there is sufficient natural refrigerant training available in Europe? And so far, 80% of the people said it's still a challenge. 20 said they're unsure, and no one says that it's no longer a problem. So I do think we have our work cut out for us. Good thing we have a textbook. So I think next up is Joachim Schadt. I had to learn how to say that. I hope I did a bit of justice. You are the hydrocarbons man on the chapter. You're going to be telling us a bit more about a hydrocarbon-chiller and how it works. So thank you. And I mean, yeah, you're the managing director of Secon, and you guys have done a lot of great work on this. And yeah, over to you. Excited to see what we can learn about hydrocarbons.
Thank you, Ilana, for the nice introduction. Now I first try to start the presentation. You can see it already?
Perfect.
Okay, super. No, I can't. Okay. Yeah, the hydrocarbon chapter was up to us because Secon is providing mainly liquid chillers running with hydrocarbons, mostly with propane. And in my short presentation, I tried to cover all main topics that are covered in the VDE book. So first point is a general chapter about hydrocarbons. Here on this slide, you see the most commonly used hydrocarbons. Propane is a kind of all-round refrigerant, let's say. It's suitable for empty, for air conditioning, for process cooling, and even for heat pump applications. Propylene is more used in middle and low temperature applications, and isobutane everyone knows from the fridges at home. And for the freezers in supermarket standalone freezers, for example. But isobutane is also very suitable for high temperature heat pumps. And for liquid chillers, it's also interesting that you can run it in a wide range of ambient temperatures. That means you can use it globally. Kind of standard temperature range is between -20 to +40, but with appropriate design and additional equipment, you can use it even in lower and even in much higher ambient temperatures. In the end, and this is now based on our product range, because I cannot talk about others, you have a very wide also a capacity range with liquid chillers, with propane in this case. You come up to 1,000, 1,200 kilowatts on air conditioning or process cooling applications, what means we do not have any relevant difference to the synthetic, to the chillers running with synthetic refrigerants. And no one must consider different use concerning capacity and also application range. Application range also means for which applications I can use such hydrocarbon chillers, and there we also have nearly no restrictions by applications. Sometimes we have restrictions because of the area where to put, especially in indoor installations, and even therefore there are solutions with small modular units that you can limit the charge of refrigerant or flammable refrigerant to an absolute minimum. What is the picture that people have in mind when we talk about hydrocarbons? Is the flammability, and mostly people also talk about explosivity, but in the end it's relevant how you design, especially about the safety concept such units. In this picture I only want to show two complete different approaches where you have two air-cooled propane chillers, and you can see that the design has a big impact on what you have to consider on the installation and the surrounding area of the installation. Of course, on the left side, you have higher cost because of more equipment and a little bit more complicated housing construction, but on the other side, you have a really controllable atmosphere and have a higher safety standard. Safety is, of course, also an issue if you do works on such units. That means the works itself are not different to a chiller running with synthetic refrigerants, but you always must be aware that you are handling a flammable refrigerant. Therefore, I put some main points that should be considered. That means, for example, that service works and repair works, of course, never will be carried out in an explosive atmosphere, and therefore service technicians should have a personal gas detector with them to have always a control and a feedback about what is happening. And if the units are properly designed and have appropriate design, you can always run the emergency ventilation during the works, so you have even a more safe atmosphere during these works. One other point always is the question about training, and there we have a clear opinion that all reputable manufacturers offer service training. We do this for installation companies that work with us, and I guess others even offer such possibilities. And of course, there are technical schools that offer special courses where they show general handling of flammable refrigerants. And at least in principle, you don't need so much many special tools, but I wrote it here, maybe the vacuum pump and the suction unit and the digital manifold should be suitable for the use with flammable refrigerants to have a higher safety level during these works. And one sidekick to environment-friendly alternatives alternatives on the synthetic side, I picked out what I call the low GWP trick of HFO refrigerants, especially 1234 Zeta A, which is still a competition to the net refs. But I guess if the truth is coming out, not only about the TFA issue, because this is already recognized, but also what happens during degradation of these refrigerants in the atmosphere. For example, that you set free HFC 23, what is one of the refrigerants with one of the stuff with the highest GWP. And if you consider this, and depending on the degradation rate, you maybe have a true GWP of such refrigerants between 700 and 1600. So they are not so close to the net refs that the chemical industry always pronounced. So what means hydrocarbons or hydrocarbons-chiller in general? You have a future-proof solution because you use a net ref. You have a wide application range available. You have high efficiency if you have an appropriate design on thermodynamic side, means if you use small delta T on the heat exchangers on the air side and on the water side, you have flammability, but on the other hand, you have no high pressures and no toxicity. And HFC refrigerants are really easily available and they are quite cheap. And as we learned before, a safe use of flammable refrigerants is not so complicated. You only must be aware that you're handling a flammable refrigerant, and you must figure out quite good safety concept. And concerning materials, we have no special requirements on the materials. It's really same material combinations like you have with HFC refrigerants. And you pleased me also to show some market development. Okay, we have no general data about the market development of hydrocarbon chillers, and therefore we give here an inside view of our development in the market, and since let's say 2017 to this year, we have a really big increase of turnover for the hydrocarbon chillers, and you can consider this market no longer as a niche market. And of course, as I told already in the beginning, we have all these main points also covered in VDE book about the net revs. The only chapter that is separate, but for all refrigerants, is the chapter about lubricants, which is also an important issue on all the natural refrigerants. So this.
Thank you so much, Joachim. We can stop sharing. That was actually such an interesting point. I think it keeps coming up that you really low GWP refrigerants aren't actually that low GWP, especially on the HFO side, if you look at the entire life cycle of it and all the byproducts produced. So I think the only really future-proof selection is naturals. And I think, like we say time and time, we're running out of excuses not to use it.
Therefore, we are very thankful about the work that Secon is doing, to spread these informations and to make the people aware that not everything is true that is written on a piece of paper.
Not everything called a fact is a fact, and I think that's why.
Alternative facts, maybe.
I think from our side, I think as Secon, we are independent. Like we've been saying for 20 years, that this is a good solution for the market. It's not necessarily because we're driving our own business or doing this for our own profit. It's just because we truly believe that this is the future of refrigeration and air conditioning. So I think, and that's why we've put in so much work to work with our wider network and putting out these fact sheets to actually just get, these are the facts,
Yes, it's absolutely right. We are not talking about demagogic things. We talk about the fact that we have to change to more climate-friendly technologies, not only in refrigeration, but especially in refrigeration.
That's the thing, and there's so much equipment in the industry. I don't think the man on the street actually realizes how much refrigeration and air conditioning affects your day-to-day life, and it really is a big industry.
There we come to the point of the visibility of our sector.
Yeah, it affects every single one of the Sustainable Development Goals. Like every single one can be traced back to our industry. So I think people need to take us seriously. Nearly every modern process needs cooling, but it's not aware for everyone that cooling, active cooling is needed. Well, let's hope. It looks like the world is waking up to it a bit more. Like now that I think it's sad that we had to come to a bit more of climate disaster for it to wake up. But I guess they always say the best time to start is yesterday and the second best time is today. So, yeah. Well, thank you. Then I think if you can stop sharing, then I'll hand over to our final presenter for the day, Thomas, and then I'll take some more questions. Thomas Bartmann is from efficient energy side, and you were involved in the water's refrigerant part of the textbook. You've also been around in the industry quite a while, before I was born. And yeah, we look forward to your presentation. Thank you so much, Thomas. Over to you.
No, thank you very much. I hope I can open my presentation even when Joe hasn't.
Oh, Joachim, can you turn your one off?
This would be great.
I could not open the video conference anymore. It's only small.
If you hidden all your, but I think it would be on Zoom.
Wait.
I can't, otherwise I can try and, I've changed it to multiple sharing, but I think then it's just going to change.
Here we go. Here we go.
Now we're back to normal. Now the floor is all yours.
Oh, you have deactivated now, Ilana.
Never now? Oh, no. Try now. Aha. Can't wait till we can go back to physical events. I'm sure they come with their own challenges.
Here we go. Thank you very much for the nice introduction. And frankly speaking, we are, as you may know, the new kids on the block. Water as refrigerant has not been considered until the last years. And the company Efficient Energy was the one to produce or to manufacture and to develop the first unit based on water as refrigerant. And now we are in the market, and the business is going well, I can tell you, because we are offering, I would say, a unique solution. Anyhow, inside the video ebook, we also have one chapter. It's a short and small chapter because our history is not that long. But I will give you today some information about what we are doing and how we are approaching into the market. We call it, and it's something that we know also from Secon, clean cooling with water, because water has some very nice features that I would like to introduce to you now. Our technology, we name it Blue Zero technology. Blue stands for water as a color, and zero means zero emissions. That means that we don't have any impact, negative impact on the environment through direct CO2 emissions. And water also doesn't provide any environmental risk. And I will tell you now why it is like this. Because anyhow, we are using standard tap water in drink water quality, nothing else. We don't need to prepare the water in a certain way. It is just especially normal water. The water is a very nice, real, natural refrigerant. Why it is like this? Zero GWP, we all are complying with that here in this event. Zero ozone depletion potential, not flammable, not explosive, it is not toxic. It has a very high evaporation enthalpy, it's highly efficient, it's an oil-free system. There are no legal restrictions. I will tell you something about the EN378 because it's not in application to us. Water is fully available. As long as it is raining, we have water as refrigerant. This is contradictory to what HFCs will have in the future. And what is very important, there are no certified inspection engineers are needed. At the end, you don't need anybody who has a refrigeration, who is a refrigeration expert. That makes us unique from others. But why it is like this? Because there are some thermodynamics features that describe water as refrigerant. First of all, the complete refrigeration cycle with water is taking place in vacuum, because otherwise it doesn't work. That means we are below 1 bar, and the temperatures we are driving now, you will see later, we are even lower. We are in this vacuum between 10 and 200 millibars. And then water is a very nice feature. It has a very high evaporation enthalpy. You can see it on the right side in this frame. And it's up to 8 times higher than conventional refrigerants. On the other side, I have to admit, as Michael showed it before, we have a very low volumetric cooling capacity, but we don't even evaporate 100% water. We just evaporate only a small part of it. And so this volumetric, this bad volumetric feature, we put it in, we turn it into an advantage for our technology. Water as refrigerant is a normal chiller. We have all the different components you need to have in the Carnot process. So we have our evaporator, a compressor, a condenser, an expansion device, and it only works, as I told you before, in this vapor pressure of water diagram only in vacuum. And in the moment we are working with evaporation temperatures between 10 and 15 degrees, and you see the pressure is about 10 to 18 millibar absolute, and the condensation is taking place around 45 to 52. It depends on the location, and up to 150 millibars. So water, don't be afraid about water as refrigerant. It's a standard normal chiller with all the components you need to have to run it. There are a lot of special requirements not needed when you consider water as refrigerant. You don't need to have, it's not flammable, so no certified fire protection training is required. You can just take anybody to do it. It is non-toxic. We don't have any safety devices in terms of high pressure switches or something inside the unit, because it's working in vacuum. Most important for the operators are no DIN EN378 requirements are applicable. And so that means no operator duties, no documentation or reporting to authorities in case of failure or leakages and so on. No machine room directive needed, no restriction on the installation setup. You can place the unit wherever you want, it doesn't matter. And as I told before, no certified refrigeration experts are needed, just trained service technicians. Important also in terms of costs, and this is also something which is important if you compare it to HFCs. The operations costs are not high due to our high energy efficiency. We are achieving high seasonal EERs. We have no high cost of maintenance. There's no oil inside the system, by the way. And we have no high cost for the refrigerant itself. As long as it is raining, I told you before, you have water as refrigerant. That makes it independent from any market developments. In terms of trainings, how are we working as company efficient energy in the moment? We are the new kids on the block. Units are available in the markets since 2018. Since then, we are selling and it's growing, nicely growing. We are working through a sales partner network, and these sales partners are trained from us. They are trained in terms of sales, in terms of explaining, arguing in the market, and they are also trained in terms of service. In the moment, Efficient Energy is the only company providing water chillers with water as refrigerant, and there's no other as a fuel product, and there's nobody else to doing this. So we are training this exactly totally on our own. We provide all the tools that our customers and the operators needs to the people. We have dedicated customer service and remote contact. We have a partner portal which is available for our partners. So all project supporting technical and marketing documents are available on there. We have local e-chiller landing pages for everybody who is interested in that. We have web apps as mobile sales tools and calculator models. And of course, we are doing events and local trade shows and like we do it here even by today. Water as refrigerant is new in the market, but it's safe and it's clean and it's energy efficient. The applications we serve, this makes us different from all other refrigerants in terms of natural refrigerants, because we cannot serve any application below 0 degrees. The sweet spot we are serving are temperatures chilled water between 12 and 24 degrees. That means we are anyhow serving the industry for process cooling. It doesn't matter if it's plastics, tire or rubber, automotive. We are making machine cooling, where we are also working with OEM partners for mechanical engineering, laser head cooling, printing machines and so on. We have everywhere, we have already references we can show to you. And of course, data centers, server rooms. You can also use it in terms of building technologies if you have chilled ceilings, chilled beams, or you have laboratories which you would like to cool. There's a wide range of application with which you can use as water as refrigerant. That's it for the moment. I hope it gives you a small idea and a small teaser about what we are doing. We are still, I would say, in the beginning of our career, but we are already in our ramp-up curve. Thank you very much.
Thank you so much, Thomas. I think you can stop sharing. It's really exciting to see that there are so much training out there available for, for all the refrigerants, because I think that is what is needed for it to actually just to take off completely in the market. I had so many questions, but I see time is catching up with us. So I want to check back on the poll. And yeah, so we had some optimistic people saying that training is not a challenge, 11%, but the majority still says that it's a challenge in Europe. So yeah, I think this book is definitely coming at the right time. I wanted to just thank all our presenters for the expert insights. I really can't wait until the book is out, and I'm sure all the presenters feel the same. It's been a long journey to this point, but as I said, I think the plan is we're pushing for December. But I mean, we'll let everyone know when it's ready. So watch the space. But yeah,
the good thing with the book is it can be used at different levels, from unit level down to the educational programs. That's I think is also a strong point.
The thing is, it's very technical. So it's not just talking about the technology and the history. It's really about how to use it and in a neutral way. So I think that's what is actually needed. So I think it's going to be exciting. Well, I mean, it's a lot of pages, but I think we cover a lot of ground. So thank you for that. I think we've running out of our time. yeah, everyone got a 10-minute break to stretch your leg before the 2-hour sessions come up this afternoon.
Yeah, just one final word, Ilana, if I may.
Please, this was your baby.
If anyone listened and you're still looking for a Christmas gift, here's the one to buy.
It is a Christmas gift that will do good in the world.
Yeah.
Good investment, I would say.
Investing in the future and for your whole team, So thank you all very much and have a